So now let's take a problem which is asked in GATE 2003. GATE AME 2003. In a Rankine cycle, in a Rankine cycle, regeneration regeneration results in higher efficiency because a pressure inside the boiler increases. Pressure inside the boiler increases. B. Heat is added. Heat is added before steam enters at the low pressure turbine. Enters at the low pressure turbine. C. Average temperature of heat addition in the boiler increases. And D. Total work total work delivered by the turbine delivered by the turbine increases. So now let's solve the problem. So in that problem, it is mentioning like a regeneration results in higher efficiency, and we know the efficiency of Rankine cycle is increased when the mean temperature of heat addition increases. So regeneration giving the higher efficiency because the average temperature of heat addition in boiler is increasing. So the correct answer is C. Average temperature of heat addition in the boiler increases. Now let's take another problem which is asked in year 2003. So I am writing the problem here. GATE AME 2003. Considering the variation of variation of static pressure and absolute velocity in an impulse steam turbine in an impulse steam turbine across one row of moving blades. Across one row of moving blades. A. Both pressure and velocity decreases. Both pressure and velocity decreases. B. Pressure decreases but velocity increases. Pressure decreases but velocity increases. decreases. C. Pressure remain constant. Pressure remain constant while velocity increases. While velocity increases. And D. Pressure remains constant. Pressure remains constant while velocity decreases. While velocity decreases. Decreases. So in that problem, it is based on impulse turbine. So remember one thing, in impulse turbine, the pressure remains constant on the moving blade. But in case of reaction turbine, the pressure on moving blade will decrease. So in that case, the correct answer will be D, because the pressure remain constant in impulse turbine in moving blades. So the pressure remain constant is right. And in the other part of D option, they are saying velocity decreases. So obviously, due to the frictional losses, the velocity will decrease in the moving blades. So the correct answer regarding impulse turbine, pressure remains constant and velocity decreases. So correct answer is D. Now let's take another example, another problem, which is asked in which is asked in GATE 2003. So let's take a problem which is asked in GATE ME 2003. So now first of all I am writing the problem here. In a gas turbine, in a gas turbine, hot combustion product, hot combustion products, hot combustion products specific heat, with specific heat, Cp equals to 0.98 kilojoule per kg Kelvin and Cv equals to 0.7538 kilojoule per kg Kelvin. Enter the turbine at 20 bar 1500 Kelvin and exit at 1 bar. The isentropic efficiency of the isentropic efficiency of turbine is 0.94. Find the work developed. Find the work developed by the turbine per kg of gas flow. So to find out work developed by the turbine per kg of gas flow. So now let's solve the problem. So first of all, I will draw the process on the TS diagram for our clear understanding. So on y-axis we are having T, on x-axis we are having entropy. Here we are having two curves. First I will represent the ideal cycle, that is 1, 2s, 3, 4s. So now I will represent the ideal cycle, actual cycle, that is 1, 2, 3, 4, 1. So this one is the actual cycle. So now first of all I will write the given things here. Cp in that problem is given 0.98 kilojoule per kg Kelvin. Cv is given 0.7538 kilojoule per kg Kelvin. P3 is given 20 bar. So I can write 20 into 10 to the power 5 Newton per meter square. That is P3 here. These are the constant pressure curves. So here we are having P3, that is 20 bar. And P4 here I am having 1 bar. So P3 is 20 bar. T3 I am having 1500 Kelvin. P4 I am having 1 bar, that is 1 into 10 to the power 5 Newton per meter square, and efficiency of turbine is given 0.94. So now we will take the isentropic, that is reversible adiabatic process. So I will write for process 3-4s, that is nothing but reversible adiabatic process. Adiabatic process. So for this process I can write T3 by T4s plus 2 P3 by P4 to the power gamma minus 1 by gamma. But here we can calculate gamma by Cp by Cv. So Cp is 0.98, Cv is 0.7538, so it will come 1.3. So 1.3. So here T3 I am having 1500, T4s I have to calculate, P3 by P4 it is 20 by 1 bar, and here 1.3 minus 1 divided by 1.3. So T4s will be 1500 divided by 20.3 by 1.3. So T4s I will get 751.37 Kelvin. So now I am having the value of T4s, that is 751.37 Kelvin. Now we know the turbine efficiency is nothing but S3 minus H4 divided by T3 minus T4. Actually, in terms of temperature, we can write T3 minus T4 divided by T3 minus T4s. So turbine efficiency is given 0.94. T3 we are having 1500. T4 we have to calculate. T3 we are having 1500. T4s we have already calculated 71.67. So T4 by this calculation it will come 796.3 Kelvin. That is the temperature at state 4, which is actual state. So now we can easily calculate turbine work. So the turbine work will be H3 minus H4. So in terms of Cp and T temperature, I can write Cp T3 minus T4. So now Wt Cp is 0.98, that is mentioned in the problem, that is 0.98. T3 we are having 1500 and T4 we are having 796.3. So Wt equals to 0.98, and if we calculate this thing 1500, we write 0.98 into 1500 minus 796.3, it will come 703.7, and if we multiply this thing with 0.98, we will get 689.626. So that is 689.626 kilojoule per kg. So the turbine work in that problem will be 689.626 kilojoule per kg. Now let's take another problem which is asked in GATE 2002. So I am writing problem GATE AME 2002. A uh, correctly designed convergent convergent divergent nozzle working at a at design load is 8, always isentropic, B, always choked, C, never choked, and D, never isentropic, never isentropic. So this one is the again straightforward question. So in theory we have already discussed like the nozzle will be always designed for maximum mass flow rate, and this condition is called choke condition. So the correct answer for this problem is the correctly designed convergent divergent nozzle working at design to always choke. So the correct answer is B, always choke. Now let's take a problem which is asked in GATE 2002. So GATE ME 2002. The efficiency of superheat, the efficiency of superheat Rankine cycle is is higher than that of simple Rankine cycle. Simple Rankine cycle, because A, the enthalpy of main steam, the enthalpy of main steam is higher for superheat cycle. B, the mean temperature of heat addition, the mean temperature of heat addition is higher for superheat cycle. C, the temperature of steam, the temperature of steam in the condenser is high. D, the quality of steam, the quality of steam in the condenser is low. So again, this one is a straightforward question, and we know this thing. The efficiency of superheat Rankine cycle is always higher than the simple Rankine cycle. So the reason behind these things is very simple. We have already discussed so many times. Whenever there is an increase in cycle efficiency, then it is possible only when the mean temperature of heat addition will be more. So the B answer is the correct answer. The mean temperature of heat addition is higher for superheat cycle. That's why the cycle efficiency of superheat Rankine cycle is more than simple Rankine cycle. Now let's take another problem which is asked in GATE 2001. So GATE AME 2001. A single acting two-stage two-stage compressor with complete intercooling complete intercooling delivers air delivers air at 16 bar, assuming an intake of 1 bar at 15 degrees centigrade. Find the pressure ratio per stage. So now for finding the pressure ratio per stage, we are having one formula. I am writing. So the pressure ratio per stage with complete intercooling complete intercooling will be equals to initial pressure into final pressure. Initial pressure into final pressure. So in that case, it will be 16 into 1. So we'll get under of 16. So it is coming 4. So the correct answer, the pressure ratio per stage with complete intercooling on this problem will be 4. Now let's talk about another problem which is asked in year 2000. So I am writing problem for GATE AME 2000. A steam turbine receives steam steadily at 10 bar 10 bar with an enthalpy of 3000 kilojoule per kg and discharge at and discharge at 1 bar with an enthalpy of 2700 kilojoule per kg. The work output The work output is 250 kilojoule per kg, 250 kilojoule per kg. Neglect kinetic energy and potential energy. Find heat transfer, heat transfer from the turbine casing, from the turbine casing to the surrounding, to the surrounding. So now let's solve this problem. So in that problem, we have to apply steady flow energy equation. So I am writing a steady flow energy equation for turbine. So in that case, I am having Q plus H1 plus V1 square by 2 plus Z1G equals to H2 plus V2 square by 2 plus Z2Z plus W. But in that problem, we have to neglect kinetic and potential energy. So on neglecting kinetic energy and potential energy, we are having Q plus H1 equals to H2 plus W. So in problem, it is mentioned that enthalpy that is entering into the turbine is 3000 and discharging at 2700 plus work done is 2500. Work done is 250. So here Q equals to 2700 plus 250 minus 3000. So we will get uh, we will get the value here is minus 50 kilojoule per kg. That is kilojoule per kg. So the heat transfer from the turbine casting to the surrounding will be minus 50 kilojoule per kg. The minus sign is indicating that heat loss from the turbine. That's why it is showing negative. Now let's take another problem from GATE examination, which is asked in year 1999. So GATE ME 1999. So I am writing the problem first here. A gas turbine power plant has a has a specific output of has a specific output of 350 kilojoule per kg and and efficiency of 34 percentage. A a regenerator is installed and the and efficiency increases to 51 percentage. Find the specific find the specific output. So now let's solve this problem. So in that problem, the specific output is given 350 and now the regenerator is installed and efficiency increased to 51%. So I am writing the important fact. On the basis of that we will easily get the answer. So important fact regarding gas turbine, gas turbine with regeneration, regeneration. Important fact regarding gas turbine with regeneration. In gas turbine, in gas turbine with regeneration, with regeneration, in gas turbine with regeneration, efficiency will increase, but work output work output will remain same. So in that problem, only the efficiency is increasing and they are asking about specific output. So specific output will remain same. So in this problem, specific output, specific output will be same. That is 350 kilojoule per kg. So the correct answer is 350 kilojoule per kg.